Time for us to start again. Just feel free to interrupt me if anything is unclear or I should repeat. So we are talking about the control, and one most important thing in the control that we need to find the value of IQ ref and the ID ref. So this means we have the torque reference. This is the torque reference we have. And from this, we need to find the value of the ID and the IQ ref for the controller. So we know what will be the torque, and also we want the speed that we know. And then we need to calculate what will be the current. Yeah, let's say we also want the speed that we know. So what you see, the first step is that we check the maximum flux linkage, stator flux linkage. And that we get it from this equation. And we see that maximum flux psi s max, which is US max divided by N. And US max is the voltage that we can obtain, the maximum voltage from the converter. And we have that voltage limited because we cannot send infinity or unlimited voltage to the stator winding. So we have the limited voltage. So this is the first step, that we check the maximum flux. And then the next step is to calculate here the current, Q-axis current. So we assume that we have the torque reference, then we can get the current, IQ, from the torque reference, then we got the psi m. We have the psi m. So from this, we got the Q-axis flux, and then we also calculate the D-axis flux, psi d, which is plus psi m, and we have the D-axis current. So it's always optimum to put D-axis current to 0. In general, we put this D-axis current to 0, and then we got the total flux, which is the psi d square, psi q square, and we try to keep it less than this. But sometimes we also need to do the field weakening, and when we need to do the field weakening, then we try to put some negative current. And we always do the field weakening that is necessary, not more than that. Because if we do the more field weakening than necessary, this means we are sending more current. Because we see that the current is the ID square plus IQ square. So if we have the more current, this means more losses. So we don't want to have the more current than necessary. Because providing more current, this means more losses. So providing more current is stupid if we provide unnecessary current there. So this is the first step, and that we present also one calculation, how we should do this, we should perform this calculation. And then we try to implement the software of the motor control. So how you can implement the control in the software that you are doing in the emulator lab, for example. So first step is to calculate the psi max. So how we are doing, we have the US max, and it's coming from the converter. Converter has the DC input. And M max is the maximum modulation that you can provide, maybe 1 or 1.15. So that is the maximum that we can provide that give us fixed US max voltage. And then we can decide what is the maximum speed that we want to run that give us psi x max. So we got the psi x max. And then next we want this torque. So this is the torque reference. This is the torque that we want. And if we see the torque, and we can represent the torque, which is psi m, and we know that torque, which is psi m, IQ, yeah, this is the torque. And then IQ you can write, yeah, IQ, which is psi q over xx. And then if you look at the stator flux, psi s, and if you have this angle here, which you can say epsilon s r, and then you can write this psi q, which is this psi q, this one is the q axis and the d axis, and then psi q you can write psi s max sine of epsilon SR. and divided by xs. So from this, we got this equation here. So we got the torque equation here based on the torque reference, and we present it in terms of the stator flux and the magnetic flux. And then we also see that otherwise we place the current vector that gives us the maximum torque, or the stator flux vector that gives us the maximum torque. So we need to find the position of the stator flux based on this equation here. So we have this torque equation, and if we solve it for this angle, a stator flux angle, and that gives us the stator flux angle, which is the arc sine of the equation that we have. So we got this angle there, and once we got this angle, that gives us the current required, ID current. If you remember, ID current, which was, it's come from the psi d, which is excess ID plus psi m. So based on this equation, we can write to this. Similarly, psi d is the same expression here. We can write something like from this. We got this equation here. So we got this angle from this equation, and we know this, and we know psi max from here, and we know this value that give us ID ref. And if it give ID ref, which is negative, if it is negative, then we will take it. If it's not negative, then we will put it to 0. So if it gives negative, then we'll take this value in the controller, ID reference. If it's positive value, if this positive value means that it's strengthening the stator flux, and we don't want to strengthen the flux. We want to field weakening, not the strengthening. So therefore, it gives you some plus ID ref, then we'll put it to 0. If it's minus, negative current, then we will take this value. So that is what we are saying here. Optimal torque control when ID ref is 0. If it is not, if we get it negative current, then we use that one. So we designed this in the software. In the software, we have the condition to calculate this ID ref current and check whether it is negative or positive. And if it's negative, then we will take it. And if it is positive, then we'll put it to 0. And then we got the ID ref current from this, and then we put the IQ ref current, the torque reference divided by psi m. So we got this ID and I ref. And also we need to check the max current total, because we know that the total current IS max should not be higher than 1. It should be less than equal to 1. So ID ref S square plus IQ ref S square, it should be less than 1. So that's how we implement the control for a surface-oriented, surface-mounted PMSM machine. First step, calculate the psi max, and the next step, calculate this stator flux angle, and based on that, calculate the ID ref. And if ID ref is negative, then take that one. If it's positive, then put it to 0, and then calculate the IQ ref. That's how we design the control in the software for a PMSM, surface-mounted PMSM machine. Any question here? So I think that is what I am also saying, that the maximum, that we have the limited current. We cannot have the infinity amount of current. And if we use more current for the field weakening, this means if we provide negative current, then we have less current for the torque production. So that's what we also say, we describe in the one of the figure, that here, when you are using a lot of current for the field weakening, this means torque is reducing. Because we are using almost all the current for the field weakening, then there is no current remain for the torque production. So that's all about the surface-mounted PMS machine. Then I want to discuss the IPMSM. I think I will not discuss those figures. Then I want to discuss the IP interior mounted machine. And in the interior mounted machine, we have the torque equation. the same torque. And we can write also the torque, this torque equation like this. You have the torque equation, then you can write psi m minus xq xd, and here is id iq. So this is the equation that we can write something also like that. So what you see for interior mounted machine, an interior mounted machine, we know that xq is greater than xd for interior mounted. Here xq is greater than xd, and the ratio is sq over xd, which is 2, we keep it something like 2 to 3 times the ratio. Sq over xd is 2-3 times. This means this one is 2-3 times bigger than this xd. So what do you see that? In the field weakening, we always provide negative current, right? Negative d-axis current. So if we provide the negative d-axis current, this means this negative, here you have the negative, then negative is becoming plus. So this d-axis current also helping to produce the torque. So that is not the case for the surface mounted machine. So the advantage is giving also the torque for this negative d-axis current. So that's why we use this machine, interior mounted machine, for traction and EB application, because when we want to have high speed, this means we have the limited flux. When the stator flux is limited, then you can apply the field weakening to achieve that speed. And again, the same current also contributing to torque production. So that's why we use this machine for EB or traction or rail, somewhere there in the transportation sector. So if we look at, we also see that the torque, we can write also in terms of this with the angle. And here, this angle actually is PP. This is the angle. And we see that based on the angle here, this is the first quadrant and this is the second quadrant. And based on the angle, we can also have the different torque. Like if we put the angle at this position for this current, you can get the maximum torque. For example, here, we can have the maximum torque. If we provide 1 per unit, and then we want to have the torque here, not at this location. It's possible if we provide the angle, this PP, at this position, then it gives us this angle, this torque, so which is much less. So we always try to operate it somewhere here so that it can provide the maximum torque if necessary. So our target is to calculate the d-axis and the q-axis current reference for the controller. And you will see that we have the same torque equation. And in this torque equation, if we replace the ID by this, and also we apply the derivative to find the maximum torque, and we derivate the torque with respect to q-axis current, that gives us the current equation like this. So you got the current equation, q-axis current equation. And from this relation, from these two relations, if you insert this ID there in the IQ equation, if you insert this ID in the IQ, then you will get also ID equation for the ID, optimum current for the d-axis current. So that's how we can calculate the optimum current for the interior mounted machine. And we also see that for interior mounted machine, what we see here, we have the q-axis current, stator current, and we have the torque and the stator flux. And we see that for this, if you increase the current, it will increase the torque. But while for the surface mounted machine, and we see that if you increase the current, after a certain point, torque is reducing. But here it's increasing the stator, it increases the torque, also it increases the stator flux. So that is the advantage of having this this machine, interior mounted machine. So now we want to see how we can implement the control for this machine in the software. If you want to implement the software, then it's more like the similar procedure that we did for the surface mounted machine. The first step is to check how much the maximum voltage that we can supply from the converter. So we have the converter, and this is the maximum voltage we can supply. And from that, we can see that this is the maximum speed that we want to operate the machine. And if we have the maximum speed, then we got the stator flux linkage. This is the flux linkage that you can get. So in the software, one thing we need to remember that we cannot put this n to 0 speed. We can never put it, because if you put it 0, then the highest become like infinity. So we cannot put it 0. We can put speed minimum maybe something like 0.1 per unit in the software. And like if you have 1 per unit voltage and then the speed is 0.1 per unit, then it gives the 10 per unit of stator flux linkage, and which is very, very high. We usually we don't ask for that much stator flux. Maybe it could be 1 or 1.2 per unit max that we can ask the stator flux max. Something like 1.2 max maybe, not more than that. So we have the first step done, and the second step, we have the torque equation. This is the torque equation that we already developed. Yeah, this is the whole term for the interior mounted machine. And if it's surface mounted machine, and we know that for the surface mounted machine, xq is equals to xd, this means this term is cancelling. This term is cancelling for the surface mounted machine, but now we have the interior mounted machine. So xd is not anymore equal to the xq. So we have now this term. If it's surface mounted machine, then it's easy only because we don't have this term, and then we can apply only arc sine to calculate this stator flux angle. We can easily calculate it for the surface, but here it's a bit different equation, since we have on cos term and we have on sine term for the interior mounted machine. So how we can calculate it in the software? We can do some method like some iteration, like we put some initial value to this one, some values, and then we perform some iteration. Usually not more than 3 times, because it takes a lot of time. If we have more iteration, then it will take more longer time to calculate this angle, maybe 2-3 times. And also need to calculate very fast, because if you remember, we have this triangular carrier wave that gives us the modulation, and we need to update the modulation index. If we have asynchronous modulation, then every this point is updating the modulation index. So this means we have a very small time, right? We have to perform the iteration within a very small period of time. If it's 20 kilohertz switch carrier frequency, then you have very small time, half of the period. So within that time, processor should calculate this angle. So 2-3 times iteration, not more than that. If it's more than that, then it cannot finish the calculation within that time. So the result will be then not realistic. So we got this angle from this iteration. Once you have this angle, and then we can calculate, based on the same equation, we can calculate the ID ref. So we got the ID ref. In the IPS, in the permanent surface-oriented machine, we say that optimum ID ref, we put it to 0. And we will compare this one and that one. If it's negative, then we will take the most negative one. But here we got this equation. It's an optimum equation for the ID ref. It's almost the same. If xq, xd are the same, then it gives us actually 0. But here for the IPMSM, we can solve the equation to have like this. It discuss more detail in the compendium how to obtain this equation, this ID ref optimum equation, but I'm not going to discuss here more detail. But it's okay for now to assume that this is the ID ref current equation that we can obtain after solving a 4th order equation. So if you solve the fourth order equation, then you got this IDREF equation, this one, and then we calculate the IDREF, either by this one, and we will take the most negative one between these two. So once you got the most negative one, then you also calculate the IQREF from here based on the torque reference. So we'll put this in the software. And of course, you also need to check the IS max, because you cannot have the maximum more current than the one the converter can supply or the stator can take. Otherwise, if it is over current, then it can damage the stator winding. So this is the equation that has been described in the previous one, the fourth order equation, how to get the IDREF current. But the final thing, what I want to say here, what I want to discuss is this figure here. So what you see in this figure, we have one torque equation, and also the smaller, we have one torque. This one is for the torque response, and this one is the stator flux response. And what you see, up to 1 per unit, is as a normal operating. But after 1 per unit speed, this is the speed. When you want to go higher speed, then you need to apply the field weakening. This means you need to provide the negative d-axis current. And what you see that, in the field weakening, you still have some torque there. So you can still have some torque for the interior mounted machine. But while if it is surface mounted machine, and we see that it was very steep, this means it was not able to provide, maybe it was here. So do you see the difference? In the field weakening region, surface mounted machine is not able to supply any torque, but interior mounted, it still can supply torque. So that is the advantage of having the interior mounted machine. So any question here after this? So just want to repeat, we have the torque reference, and we have the torque reference, and based on the torque reference, we calculate the IDREF and IQREF. So that is the main purpose of our control. So once you have the IDREF and IQREF, then you can use the IDQ current controller. This is the current controller that we have already seen for the synchronous machine or the DC machine. This we can have the current controller, PI controller, but we need to understand this part. We have the torque reference, and we have the stator voltage, and we have the maximum stator flux linkage. Based on that, we need to calculate this torque, d-axis and the q-axis current reference. So once we have the d-axis, q-axis current reference, then we can implement the control. So now so far we understand how to get the d-axis and the q-axis current reference. Once we know how to get this d-axis, q-axis current reference for this TU machine, then we are now ready to implement the control, the current controller. So in order to implement the current controller, you also need to understand the dynamic equation of the converter. And here we have the two first order equation and how it comes. If you remember, UD from the dynamic equation, it was Rs ID plus 1 over omega n d psi d dt minus n psi q. I think you remember this equation. And here, psi q is this, and psi d is this. So if you insert these two equations there, psi q here and psi d here, this psi m, magnetic flux is constant. So derivative of this magnetic flux is 0, right? If you insert it here, and this xd is constant. So only this is the variable, and this one is also constant. Since it's constant, then if you put it here, then it's 0. Then if we rearrange this equation, then it will come up to this equation. If we rearrange, then we can write did dt, here this, and diq dt, like that. So one interesting thing here, what we see in these two equations, we have some cross-coupling term. Even though this equation is an equation for the d-axis current, but we see that this term here is related to is something coming from the current, the q-axis current. And here, this term is also coming from the d-axis current. So you have something cross-coupling term here. And also you have something here is we call it feed-forward term, if you remember. So you have one feed-forward term here, and the two cross-coupling term. And this UD and UQ, they are the control voltage of the machine. So this is the voltage that we will provide to the machine so that we can control the d-axis and the q-axis current. So we try to implement the current controller that control these two current, ID and IQ, based on the two input here, UD and UQ. So we have the dynamic model. Yes, this is the block diagram representation of the dynamic model that we see in the previous slide. If you have the dynamic representation, and then you have the dynamic model in the block diagram. So you have this UD here, and you have the UQ, and here we implement the control part. This is the controller that we implement, like one PI controller for the current reference, and some cross-coupling terms, some feed-forward term that give us UDU control signal. So you have the dynamic model, and based on that, we will implement the control. And we see it has some feed-forward term and some cross-coupling term. So we try to neglect, this is the cross-coupling term. So we try to cancel the cross-coupling term. Since you can see we are adding this plus here, then we will put something minus the same component here. Then it can cancel. That's what we did to neglect the effect of the cross-coupling term. So we can represent the control voltage, this control voltage here, the input voltage to the machine, with two terms. One is the PI controller. The first term, DI, is the PI controller term. And the second term here is from the feed-forward term and the cross-coupling term. In the first one, we have only the cross-coupling term, which is N, XQ, IQ. And the second one, in the Q-axis controller, we have both also cross-coupling term and the feed-forward term. So this part, the second part, is the cross-coupling and the feed-forward. So we insert this feed-forward and cross-coupling term, and they cancel from the original equation. If they cancel from the original equation, then we come up to this decoupled model. So, and then finally, we come here to this decoupled model. This means we can neglect the effect of the cross-coupling term here. So now no cross-coupling term because we are canceling them, and also we are canceling them, adding the additional as we discussed. Then finally, we'll have two first-order equations. And these two first-order equations, if you remember this machine, and we have one field current controller. This is the field, and one is the armature. Yeah, this one I can say IF for the DC machine. And the armature one we are using to control the torque. So we can use the current to control the torque. And we can use this equation to control the field. Because if you provide the negative d-axis current, this means it's controlling the field, it's weakening the field. So now we have the two decoupled equation that you control to control the torque and control the field. So it's now behave like a DC machine. It's almost like a DC machine now. we have the two separate equation, two decoupled equation. So this is just a block diagram that built in Simulink. And we have PI controller with the one that we discussed in the control and filtering lecture. So you have two separate controller, one PI controller for D-axis, one PI controller for Q-axis, and we have one decoupled term, so we can neglect the cross-coupling effect such that they operate as a they can neglect the effect of the cross-coupling term. So this is just a representation. Maybe Roy uploaded this in the Blackboard, so you can also simulate. I'm not sure, but this is just a representation of the machine in the Simulink. In this slide, what we want to show, like we have the machine model that we have developed. If you look at the original machine, this is the original machine here. In this is the original machine, real machine. And from the real machine, what we have, the output we are taking is the current. This is the current that we are taking from the machine. And we are giving a stator voltage. This is the voltage that we are giving. So in this block, we have the real machine, and we are measuring the current, and we are giving it feedback to the controller, and we are giving voltage, this from the converter. So when we did the modeling, what we do, the stator voltage, we apply the transformation, then we got a DQ, equivalent model. So even though we are giving three-phase here, then we have this transformation, then we have everything in the DQ. And then again, in the model, we are applying inverse Laplace transformation here. So we have the DQ here. Because of this inverse Park and Clark transformation, we are getting the current in the three-phase AV system. And this current in three-phase AV system, we are giving into controller, again applying transformation so that we are getting ID and IQ. So what I'm saying, you are getting the current at this point, they are in ABC frame. But in the model, in the here, they are in DQ frame. So you have ABC, and again, we are applying transformation in the controller, we have in the DQ. So what you see that, you're originally getting DQ, and here in the controller, it is DQ. This means controller see a DQ model. It doesn't see the ABC model. Controller will see that it's a DC machine in the controller because it's canceling these two transformations each other. Then controller C is a DC machine in the controller. So it's similarly also here from the controller we are giving UD and UQ. Then we are converting here and we are getting UABC. And again, here it is UD and UQ. This means if we cancel these two, so this is from the controller, and controller C originally is actually DQ model. So that is what we want to say that the controller, we have the controller here somewhere, and the digital controller, it sees only this model that we build up, the mathematical model, because of this canceling effect. So now it's time for us to design the control. And this is the same principle that we apply in the DC machine or controller filtering circuit, the modulus optimum tuning method. So what you see, we have this term from the controller, this is PI controller. And we have this term from the machine side, inside the PWM is PWM delay or the filter. And this is the machine dynamics. So if you look at the block diagram, since now it is decoupled block diagram, so what you see, you have the current reference, this is the current reference. And you have the first PI block. and the delay block. And then you have the part from the machine, which is like TD 1 plus STD. And then that gives us the current. Like maybe it's ID current, and then you're getting ID current. Since we added the cross-coupling term and the decoupling term, and they're canceling, and finally we come up to this equation. Because all the cross-coupling and decoupling term, they are cancelled because we feed forward and added them, decoupling term, and it got like this. And from this, we got this open loop transfer function. So we got this open loop transfer function. Once you got this open loop transfer function, then you can apply the modulus optimum tuning method, like cancelling the pole with one of the 0. This you cancel. And this is the method that we discuss in all other control part. We are cancelling. This means we put TID equals to the same TD. And the TD is from the machine. It's machine data. Then we also set the damping factor. If you remember, damping time constant, which is 1 over s square root of 2 in the second order equation. And that gives us finally the proportional gain here. So you got the proportional gain for the D-axis current controller and also the gain for the Q-axis current controller. And here we have the TB plus TFD is the T sum. Here this part, which is T sum. And T sum, one is because of the PWM delay. So the first part is because of the PWM delay, and the second part is because of the filter. Since you also have a filter there in the control, yeah, we also have one filter here. And then you have to find the filter time constant. This filter time constant, and if you remember the filter time constant, how we determine the filter time constant, we check the modulation, we check the voltage and the ripple voltage for the full bridge converter, and we see that for the D-axis and the Q-axis, the ripple voltage we can represent like this equation. That is what we have already discussed in the controller and the filtering chapter, and we see that for the D-axis, we can write it as a ratio of this filter time constant and the switching time constant, the carrier switching time constant, carrier frequency time constant. So we try to limit this voltage, this ripple, not more than 8%, maybe 4 or 5%, something like that. And that's how, if we know the frequency of the carrier, triangular, then you can calculate the time constant of the filter. So this is one example here, you can see. And if you plot this equation here, if you plot this equation, then you will see that we can calculate the time constant from this, like something here, maybe 8%, not more than 8%. If it's 8%, I think it's somewhere here. If it's 8%, maybe it gives us something like TFD over TSW. So this is USTD ripple. And here in this axis, it is TFD over TSW. So if you limit the ripple somewhere at this point, 8%, and it will give you TFD over TSD something like 0.01, 0.01. So from this, you know TFD, which is 0.1 multiplied with TSW. And TSW, which is the carrier frequency, 1 over FSW. So now let's say you have the delay. This is T sum. This is the T sum. And you have T sum, which is TFD plus TB. And now let's say we got the TFD, which is 0.1 time TSW, and the PWM delay, which is, let's say, 1/3 of switching frequency, let's say 0.33 TSW. Then you are getting T sum, which is 0.43 TSW. And if you remember from before, if we set something reference like this, and how long it takes to reach this value, and here the rise time, which is 4.7 times T sum. The rise time is 4.7 times T sum. And here T sum, which is 0.43 times TSW. So in order to increase this rise time, if you want to track the current instantly, this means what you can see from this equation, you need to reduce this T sum, only the value that you can reduce here T sum. And here T sum depend on the T switching frequency. This means if you reduce this value, the switching time period, if you reduce this value, this means you are increasing the switching frequency, right? So if you reduce this TSW, this means you are increasing FSW, switching frequency. So if you increase the switching frequency, this means that you can have faster response from here. Any question here? And the previous one, we also discussed that if you have a digital controller, then you also need to consider the sampling time of the digital controller when you calculate the time constant, integral time constant of the PI controller. Similarly, this part also coming to the proportional gain here. And that's what we have discussed before in the other chapter. So it's for the digital. If it's analog controller, continuous controller, then it's as it is. But if it's digital controller, then we also need to include the sampling time there. So we apply symmetric modulus optimum for the current controller. But for the speed controller, this is the part for the speed controller. And you can see it's an integrator for the speed controller. And the speed controller give us the current reference, the Q-axis current reference there. It gives us actually torque. And when we divide the torque with Cm, that gives us the current reference. And it's the integrator that we have here. So when you have this integrator, and if you remember what method we need to apply to tune the controller, and it is symmetrical optimum method that we need to apply. So if you apply the symmetrical optimum method, then you can tune the controller for the speed controller. Yeah, I think I don't need to discuss in detail how we tune the controller using the symmetrical method that we have already discussed. So you can apply the symmetrical tuning method here. And then if it's a digital controller, and you also need to control the speed sampling time, the sampling time of the speed in the controller gain. So that's what I have for PMSM machine. And if you have any questions, just feel free to ask. And otherwise, thank you for joining the lecture today. And there will be no lecture on Monday. sorry, not Monday, Thursday, but I will see you on Monday again, next Monday.